Alright, here are solutions for perfect problem 5 from Math 251. What we're going to use is we're going to use implicit differentiation a bunch of times, 5 times I think, to prove various facts. So the first one here is kind of saying prove the product rule. So it's writing out the product rule really explicitly here, saying the derivative of f of x times g of x is f prime of x times, okay, all this stuff. So what we can do here, kind of following the hint, is it says start with y equals f times g. And just make sure you know that y, f, and g are all functions, right? F of x and g of x. And we can't just take the derivative of both sides right now because we don't know the product rule. It's what we're trying to come up with here. So we can't take the derivative of something times something. The way you can turn products into sums, I guess is a way to think about it, is by taking the natural log of both sides. So if you take the natural log of both sides, you get here, which we still can't deal with because we still have this product in here. But if you take it one step further and recognize that the natural log of a product is the sum of the natural logs, this is good news. You've come a long way because we can now take the derivative of both sides of this equation. Take the derivative of the left-hand side, you got chain rule here. Outside functions natural log of x, inside functions y. So we get 1 over y prime using the chain rule. Similarly, derivative of natural log of f and natural log of g will be 1 over f prime and 1 over g prime. These are all chain rules. Outside function is natural log of x. Inside function is f, g, or y, as we specify up here. And let's see, we know that, well, I guess you have some options. You can multiply both sides of the equation by y here to get y prime all by itself. So sure, let's do that. That would give us y prime equals y f prime divided by f plus y g prime divided by g. However, y is f times g. So instead of writing y, I can write f times g times f prime over f. And same thing, instead of writing y, I can write f times g prime over g. And what happens now? Got an f up top and an f on the bottom. G up top, g on the bottom, those cancel out. And when all the dust settles, what you have is the product rule. We have on the right-hand side here, could rewrite as f prime g plus g prime f, which is exactly our product rule here. I'll just say y prime. Since y is f times g, what we've shown is y prime is exactly the product rule. Maybe I throw a box around this, put a little check by it, something, I don't know. I think a check will suffice. No, because that looks like a different letter. Alright, let's throw a box around it. And we've just proven the product rule. It's kind of cool that you can prove the product rule if you didn't believe the proof we did earlier in the class, just using implicit differentiation, really logarithmic differentiation. Okay, part B says do the exact same thing, but now with the quotient rule. Probably go a little bit quicker this time because it'll be very similar to the above, as the hint says. We don't know the derivative of f divided by g, but what we can do is get rid of that quotient by first taking the natural log of both sides and then recognizing that the natural log of a quotient is the same as the difference of the natural logs. And this is really good. We can take the derivative of the left and the right hand side and get 1 over y prime equals 1 over f prime minus 1 over g prime. Let's jump up top here. Y is equal to f over g, so 1 over y is g over f. So I have g over f times y prime is equal to f prime over f plus g prime minus g prime over g. And now multiply both sides of the equation by the reciprocal here, so multiply by f divided by g. And what you get is f prime f divided by fg minus fg prime divided by g squared. These f's cancel out, and to get well, I'll do it in 2 steps. When the f's cancel, you get here. And if you find a common denominator, you get f prime g over g squared minus g prime over g squared. Oh, f g prime. This f right here should have gone here, and should have gone here. I just didn't copy the same letter all the way down. So you get to here, and we can now write this as the quotient rule. The quotient rule says the derivative of f divided by g is f prime g minus g prime f all over g squared. And so we've managed to prove the quotient rule. Okay, now prove the fact that the derivative of natural log of x is 1 over x using, well, I guess it doesn't say what to use here, but we'll see what to use. So start with y equals natural log of x. We want to show that y prime is 1 over x, and the way we'll do that is by doing e to both sides of the equation. E to the natural log of x is equal to x, because e to the x and natural log of x are inverse functions. And if you now take the derivative of both sides, we have to use the chain rule on the left. So we get e to the y prime equals 1. The derivative of x is just 1. Another way, let's jump up here. If you solve for y prime, you get 1 over e to the y. Oops, e to the y. But we don't want to solve for the derivative of y in terms of y. Fortunately, we know that y is equal to natural log of x. So we could say that y prime is equal to 1 over e. Oh, you know what? Let's get even clever about this. Instead of substituting in for y, let's substitute in for e to the y. E to the y is equal to x, so we just get 1 over x, which is the derivative here. You could have shown one extra step. You could have substituted in for y here, and you get e to the natural log of x. But again, e to the natural log of x is just x. So either way, you get to this point. All right, moving on, part D. It's time to change colors. Part D is very similar to part C, except now it's not natural log of x. We want to find the derivative of its log base b of x. That's okay. We can do the exact same thing. Start out with y equals log base b of x and try to find y prime. The way we'll do it is raise b to both sides of the equation, as the hint tells us. B to the natural log of, well, I'll write it. B to the log base b of x is just equal to x. So if we now take the derivative of both sides, on the left-hand side here, we have to use the chain rule. The derivative of b to the x is b to the x natural log of b. So the derivative of b to the y is b to the y natural log of b, but then you're not done. You have to multiply by the derivative of the inside function, which is y. Its derivative is y prime. So you get to here. You want to solve this equation for y prime. The way you do that is divide both sides of the equation by all this mess here. And that gives you y prime is equal to 1 divided by b to the y natural log of b. Which is great, except you don't want your answer for the derivative of y to be in terms of y. You want it to be in terms of x. But fortunately, we know that b to the y is equal to x. So we can, instead of writing b to the y right here, we can write x. And what that gives us is exactly what we wanted. That the derivative of log base b of x is 1 over x times the natural log of b. All right, last one here. Oh, this one. Okay, so we're trying to show that the derivative of arctangent is this mess. I think we did arcsine. We might have done arccosine also in class. So we can kind of follow that method. The basic idea is start out like we did above by letting y be equal to what we want to find the derivative of, and then what we'll try to do is find y prime. Problem is, you can't take the derivative of both sides because we don't know the derivative of arctangent of x. Like, yeah, we do. It's this right here. Well, right, but that's what we're trying to prove. We can't use what we're trying to prove. Otherwise, we're just kind of going in circles logically. So what we can do is take the tangent of both sides of the equation. That gets us here. And now we can take the derivative of both sides because we know the derivative of tangent of x is secant squared of x. So the derivative of tangent y is secant squared of y times y prime. And that's equal to 1 because we took the derivative of both sides of the equation here. On the left-hand side was a chain rule, inside function was y. So we can solve and get y prime is 1 over secant squared of y. Maybe I'll write it like this. It means the same thing, but a little bit more clear what we're doing here. Which is correct, the right answer and all, but we don't want the derivative of y in terms of y. So let's substitute say, all right, y is equal to arctangent of x. So I could say it's the secant of arctangent of x, that whole thing squared. That's better, but it's still not simplified. We want to get it in this form right here, but we can get it into that form right there. I should probably change colors, make sure I got lots of room up here. We want to simplify secant of arctangent of x. And the way we'll do that is by looking at arctangent of x, maybe giving it a name. Let's call it t. If arctangent of x is equal to t, we can take the tangent of both sides of the equation and get x is equal to tangent of t. And if x is equal to the tangent of t, what that tells us is that if we draw a right triangle here, and this angle is t, SOHCAHTOA, the opposite side over the adjacent side to this angle is equal to x. X over 1, maybe, if it's easier for you to think about it like that. So opposite over adjacent has to be x. We can call this x and this 1. And we know two sides of this triangle. We should probably figure out this third side because maybe it'll come in handy. It'll definitely come in handy. Pythagorean's theorem. This squared is equal to this squared plus this squared. So this is equal to the square root of this plus this squared plus this squared. 1 squared is 1, x squared is x squared. So now we know this. Let's see if that's enough information to get us our final answer. Over here we're saying that what we want, y prime, is 1 over the secant of arctangent of x, but arctangent of x is just t, so it's the secant of t squared. And we can figure out what secant of t is by looking at this picture. Let's see, secant is 1 over cosine. So SOHCAHTOA, cosine is adjacent over hypotenuse. So secant would be hypotenuse over adjacent. In other words, secant of t is the square root of 1 plus x squared. So what we get, instead of writing secant of t in here, I can write 1 plus x squared. Square root of this thing squared, which you can then simplify. Got to be, well, okay, you can cancel out the square root and the squared. Can't really do that. You're supposed to replace it with an absolute value sign, because when you take the square root of something, well, let's see, no, I guess this would have to be positive. So we can just leave it just like this. This is the right answer. It's exactly what we wanted the right answer to be. So we have that the derivative of arctangent of x is equal to 1 over 1 plus x squared. Put a little check mark by that, and we're done with this perfect problem.